All right. Hey, everyone. Welcome back. Let's see. I thought I was prepared, but I'm not quite as prepared as I thought I was. So here we go. Let me share the screen here. All right. Let's see. Okay. All right. Now we're cooking with gas. Cool. All right. Yeah. So, wow, what an adventure, right? Anyway, I'm Paul Baylog. Welcome to the Go Meetup, and I'm going to try to click through slides here, the ones that I do have. There we go. All right. And then I'm joined by Sabri, and then Brandon should be joining us here shortly. And then Siju, I think he might be coming up online too, but we are your steering committee. And yeah, my little sponsors page here. Yeah, pretty much everything's gone off the list except for meetup fees, which are covered by GoBridge, and I guess the Crowdcast supplied by me. So hey, I got to put my name up there. So anyway, let's go into the normal little what gives, see what's going on. So I guess since the last time we all met, the Go survey came out, the user survey, and it was pretty cool. I mean, I was looking through some of it, you know, not a whole lot, but it was pretty impressive. They collected a lot of data. I forgot actually some of the details on it now, how many respondents there were, but it's kind of interesting. I mean, you know, it's definitely growing, so, which is a good thing. So, yeah, this I think they're still claiming it's postponed for the GopherCon. We'll see if it actually happens, but would be kind of cool. But yeah, no, probably not. And this slide I happened to actually forget to remove from this because last week when we were going to do this, it was going to be this past weekend, but 3 a.m. St. Louis time. So I don't know if you're really into it as zealot, then you could have participated. So anyway, we've had a little bit of Murphy's Law going on, all kinds of problems, just yeah, nothing working out. So we had to change it up today. So we got due to Murphy's Law, we're just going to have like a Q&A session essentially. Brandon, who is still not here yet, he suggested that we go ahead and just kind of do a Q&A session since we can't do a presentation, the normally scheduled one, which hopefully Sabri will be able to do that one in June, I'm guessing then. Because yeah, next month we've got somebody lined up. So anyway, yeah, we'll see how to do this. Who's got questions? Just, you know, down there in the bottom, there's the question, or just, oh yeah, Dave's here just for the free pizza. That's the pizza is virtual, so hope you enjoy it. It's the question though becomes is you know, should it be St. Louis style or Chicago deep dish or something? So yeah, we'll leave that up to you guys, but yeah, so please, any kind of questions. I mean, and what we want to get to also is like, what kind of, I don't know, what kind of presentations would you like to see in the future? Next month, like I mentioned, we've got, it's kind of more of a cloud native discussion. It's Daniel Mangum, sorry, he's on the, is it Crossplane, I think, open source project. It's kind of a Terraform on steroids in a way. It's kind of building up your infrastructure and all that. He's going to be talking to us next month on that. So that's going to be really cool. But yeah, if anybody can suggest anything that they'd like to have presented, or, you know, or even a problem, if you got a problem that you're stuck on or something, Sabri's here to help you out.
I sure am. No, I'm trying to get a lean coffee thing set up here. But my neighbors are very loud because, of course,
Uh-oh.
I live downtown. It happens.
And by the way, Bud Light Seltzer is not an official sponsor. So, yeah. I figured it's light and fresh, so try that.
Cool. So hopefully folks will have... So I posted a link to Lean Coffee for the meetup. We can use that if you're familiar with Lean Coffee.
I am not.
Cool. So Lean Coffee, kind of a format where you can allow an audience or a group to post questions. Then there's like a voting sort of thing. And we create, I think it's like a default, like a 5-minute timer or something for each topic. And then we can vote to extend the timer or to move on. It's just a nice little way of facilitating discussion.
Oh, nice.
And hopefully that link will get people access to it.
All right. So just, I guess, create an account and in here.
Yeah, you shouldn't need an account. Let me... This is very seat by pant. Let me see if I can...
Yeah, I'm starting to think that nobody would expect any less from the Go group right now. So,
here it is. I will.
Do you want to share your screen? Is there going to be something on there that we want to
eventually?
share,
Yeah.
or?
Let me see if I can give people the right link so people can not have to sign up. There we go. That looks, yeah, guest equals true. That's better.
There we go. Okay.
Technical questions, community, any kind of question that relates to Go, kind of, even if it's somewhat tangentially, because we're here about community and stuff, right? So that should give folks access to that, and so you can add new topics, and then, like I said, we can vote on existing topics, and we can kind of facilitate that way. Cool. I see guests, so that means you can do it. Cool. That's good.
Yep. John Vilmer's asking if we can have an impromptu discussion about concurrency, since you are the concurrency expert.
Oh, no. Sure, we can have if you want to talk about concurrency at a very high level, we can definitely do that. So like a less than formal concurrency talk, I think would be.
Yeah, because I think we did a poll on the last one where we were kind of like, it seems like we're mostly kind of new to Go. So yeah, even myself, I mean, I've been playing around with it a bit, but contributed to a couple projects, but I am by no means an expert. So.
Let me refresh.
And actually, let me pull down that display. So
cool. And there are a couple of people just joining. So there's a link in chat. I'll post it again. Cool. It doesn't let me send it again. Okay.
Let's see.
I think it's like an anti-spam thing.
I can delete the first one. There we go. So the incorrect one has been deleted. So
cool.
If you just look up in the chat history, you should see a link.
Yep. And I'll add concurrency to the board. Cool. You should add something, Paul. What would you like to talk?
Here, I'm going to vote for that. The concurrency. There's my vote.
This is like I wish there was a whiteboard feature of Crowdcast. It would be fantastic.
That would be pretty sweet. Yeah, I know. With some of my from a previous life, we got together for a little happy hour, and then we were using Zoom, and they've done some little bit of updates since they had all their Zoom bombing issues.
Yeah.
Yeah.
Yeah. It's been bad. There's been quite a. I don't want to have to do all this. Fine. I'm trying to get a whiteboard up very, 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 very quickly. Let's see.
Nothing like putting you on the spot.
You know, it's fine. Lots of free trials that I have to delete. No big deal. Don't want one. Okay.
You know, and I'm going to just throw this out there too, that just in case for those that don't know, we do have a GitHub account. And then ultimately we'd like to start throwing in some, you know, some fun projects or something like that, just for learning and all that kind of good stuff. Anyway, Spree just threw out another link.
That is our whiteboard.
All right.
Oh boy. Cool. Writing security specific test cases. That's a good one. Any other topics? Well, I guess we can kind of get started with the first two that we have.
Cool.
Wonder Brandon is running.
Did you make it on?
Yep. Okay. Well, I posted a link to Whiteboard that we can use to discuss things. And
all right.
So about this Go concurrency thing. Oh boy. So I wish there was a good sort of like introduction to Go that I can kind of like copy pasta. But so Go concurrency is a little bit unlike concurrency. And so if you're coming from like a Java or C++ or JavaScript background, so there's kind of two, maybe three different prevailing sort of concurrency methodologies right now in modern programming languages. There's the first, which is kind of like, I think probably the most common right now, which is futures and promises. And that kind of, you know, it's effectively a state machine, but it's a way that a lot of programming languages, including like a JavaScript that aren't necessarily multi-threaded, kind of pretend to allow for concurrency. And so it's sort of like, you know, very micro context switching. It's a very small state machine. I won't go too far into promises or futures, but that's for another talk. Go isn't that way. And so Go's concurrency, I think, is often compared to like the actor model, where there are different actors and they send messages back and forth. Yada, yada, yada. That's pretty close, but it's not quite the sort of like the formal groundwork for Go concurrency. I will see if I can find a good primitives list here. Maybe not. So here we go. All right, so I'm just going to post this into chat because this is actually a really good sort of intro to Go concurrency. Oop. This is one of the better ones that I found. It's the official sort of introduction to Go concurrency. And I guess what we can actually kind of do is sort of go through one of these examples, maybe visualize it. That might be helpful.
Here, do you want to share your screen, or do you want me to share?
I can share my screen. Maybe. This is not a computer I'm used to working on. Let me see if I can.
So yeah, so last week what happened was your liquid cooled CPU went out.
My graphics card died.
Okay.
So it's fun. No, the fact that it's liquid cooled only matters because taking it out means I have to drain everything. Woo. So yeah, that was fun. But I have a replacement coming eventually. Yeah, I ordered toilet paper like 3 weeks ago, and Amazon still hasn't gotten it to me. My graphics card is not priority. So let's see. Maybe that'll work. Okay, I think I shared.
Wait.
I see a video of my screen in it.
Yes. There we go.
Yay.
Technology.
Okay. That's pretty meta. Okay, so if you haven't clicked on the link yet, this is sort of the concurrency I have on weird dark mode stuff. Let me turn this off. Okay. Actually, let me turn that back on. So if you're new to Go, like I was saying before, if you're coming from a previous sort of programming experience, I think, again, two of the primary paradigms that you'll see are futures and promises, which are common in things like JavaScript, TypeScript, and things like that, which are kind of a way of like enabling concurrency-like things in a single-threaded or like a limited-threaded environment. If you're coming from C++ or maybe even like older school Java, you're probably more familiar with like multi-threaded programming. So if you wanted to, spin off a separate task or procedure, you would create a thread or use a thread pool, and that thread would be started with the function yada yada yada. Function yada 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 would run until completion, and then that thread would be returned back to the operating system. Go is a little bit different, and the way that it's different actually makes it very, very high performance or high performant when it comes to concurrency, and also very, very lightweight. And so let me see if I can find good. Yeah, well, this is Wikipedia, so this might not be helpful. That's not helpful. And so Go is green thread. That's useful. Go is kind of based on the idea of green threads. Or Go concurrency is built on top of green threads. And so you may have heard about this in other, actually Go and Erlang are users of this technique. Called out specifically, you may have heard of this sort of idea in other programming languages as well. But green threads, as opposed to sort of like, operating system threads, which are managed and scheduled by the operating system, are sort of like these smaller constructs that are managed either via virtual machine or a language runtime. And so if you don't know, Go has fairly significant runtime. It's definitely smaller than like, say, the JVM or something like that, but definitely comparable to maybe like the C++ runtime. And so within that runtime, there's a scheduler, that schedules and sort of determines where green threads are. It may sticky them to a particular thread. Multiple green threads can be scheduled on a single thread, yada, yada, yada. And so you can fit a lot of concurrency without using a lot of threads. And because creating threads are kind of expensive, it's slow, and you have a limited number of them based on the operating system. And having lots of threads isn't really effective if you're in like an embedded environment or low cost virtual machines and things like that. So I will post this in chat as well if you are interested in sort of like some of the specifics about green threads. And so there are a lot of the Go runtime and how it schedules green threads or these like micro threads has changed over time. I won't get into that right now because if you're a beginner to Go, you probably don't care. But the only thing I would kind of say about that is that it does have some methods to prevent starvation, which effectively means if one of the threads is stealing resources or is ongoing, the Go runtime knows that other things have to run. And so it knows how to sort of steal time to distribute across different threads, or Goroutines more specifically. So that's kind of the basis of that. Let's go back to sort of the concurrency page. And so again, I'm kind of just going to go over this at a super high level in my own words because I don't want to give the talk I was going to give. That was a lot. That's a lot more in depth than this one. But Go's concurrency primitives are very Go specific. So you don't see things like threads. You won't hear promises or futures or anything like that sort of in the Nomicon. What you instead hear are things called Goroutines and channels. And this is actually, so this is a pretty decent page that kind of explains the nomenclature a little bit. And so, to quote, a Goroutine is a function that is capable of running concurrently with other functions. That isn't the most useful thing. But to create a Goroutine, we use the keyword Go followed by the function invocation. So if you've ever seen, let me see if I can make this bigger. Yeah, there we go. My screen is 4K and it might be really small for you guys. Cool. So
maybe
I'm sorry.
Maybe one more.
One more.
Zoom in there.
I'll just keep going. Cool. So the thing about Go concurrency is that it's extremely easy. So because it is sort of like a first-class member of the language, you can turn any sort of function invocation, in this case f, which takes an integer, into something that's concurrent by putting Go in front of it. That's it. And it really doesn't get any more complicated than that, even if you're starting to go out, and do more complicated patterns, more complex concurrent interactions. This is what you do. And so the Go compiler will know that, that will create a Go routine. And it knows that this will be scheduled in the background, and it'll pretty much take care of all the scheduling and all sort of like the piping behind the scenes for you. So because it's this easy to get started with concurrency, and Go uses it very liberally, right? It is very lightweight to do that. And so that's kind of if you in a lot of cases in like C or C++ world, you just have a long running or short running task that you want to have in the background that doesn't block the primary function or the context that you're currently in. This will do that. One thing that I think is maybe, well, let's not talk about that yet. Yeah, let's not talk about that yet. Let me see if I can find like a better example. Probably not in here. Okay. I think one of the important things in sort of in the context of Go is that, let's say function f was an extremely long running task. How, you can imagine here that this may outlive main. And the Go runtime knows how to sort of deal with that. But let's say if you're, let's see if we see if we actually have like a explanation here. Probably not. No. But Go routines themselves don't block by default. And so in this case, if f was some long running function, main won't block for the completion of that routine. And that's a little bit different than say like using a future or promise, which you have to explicitly await on. So hopefully that makes sense. I won't go into CSP too much, but let's go into channels. So channels are sort of like the default mechanism for Go routines to communicate. There are other ways to do this. If if you're coming from C++ or Java or maybe some of the other languages, you may be used to mutexes and things like that. For those things still exist in Go, but you won't see them as often. And the primary reason for that is sort of idiomatic Go concurrency is heavily relying on message passing. And so the talk that I have prepared is actually on CSP, which is sort of like the formal. Well, it's formalized, but there's like 3 different formal variants. It's really, really confusing. But it describes how different routines or different sort of concurrent processes send messages to each other. And they wait for messages, and then they process that message, and then send another message and process that message. So there's a lot of sort of like benefits to that, and there are some drawbacks to that. And if you can sort of like read this example, there's a pinger and a printer, and I'm, creating these 2 things, and they're sending. This is sort of this little arrow is the built-in syntax for sending things through a channel. One of the benefits, and I'll try to keep it a little bit higher level here, is that it's very easy to come up with patterns that are easy to explain, right? And so if you're thinking about a process or some sort of like, moderately complex interaction, you can probably break it down into steps, right? And here's, 2 or 3 things. And actually, this might be a good time for a whiteboard. Let's whiteboard. Yeah. Let's see if I can. I haven't. Oh, yeah, this is weird.
Yeah, it's kind of funny because, with concurrency being one of the central things in Go, the little that I've done, I really haven't done anything at all with the concurrency stuff. The only thing is like, maybe starting up the HTTP server or something, wait for done and that, but that's pretty much it. I really haven't delved into that world a whole lot.
Yeah, it's different than, again, like sort of like the other concurrency models. In fact, like even using the word concurrency over like multi-threaded has sort of changed in recent times, because multi-threaded was sort of like the default paradigm.
Right.
And Go was like, well, threads are too fat, so we're going to make something smaller and just use green threads. But it does have some benefits. So, we can sort of, let me visualize. This may or may not be. Well, let's just go with it.
Yeah, I see some eyes looking at me. Okay, they're not eyes.
There we go. So I'm going to break into something that might look very UML, but like, so let's just say we have 2 Go routines, and these little circles represent different Go routines, or let's say 3 Go routines. Let's make it kind of realistic. Cool. And so the first Go routine, and so effectively what I'm going to describe to you may be implemented as like a work queue and sort of like other languages, and you'll kind of see what I mean here. And so let's call this a doer. So Go routine is number 1 is a doer, and Go routine 2 and 3 is a queuer. I don't think that's a word, but we'll go with it. I don't know how to spell queuer. There we go. That's sure. Let's go with that.
QER.
Yeah. QER. There we go. So the way the primary sort of interactions in sort of Go world are, again, through channels. And so if channel 2 and channel 3 are sending messages through channels to Go routine number 1, right? And Go routine number 1 has to process that income message and, do something, and then it blocks, right, for that process of that one thing, and then it waits for another thing. And so what it typically ends up looking like, and let me use a different color for this, maybe I can do that. Cool. Let's use these for channels. Right. And we're going to, let's say these are strings that it's sending. Foo.
Oh boy. Yeah, that color does not come through well.
I will not use it. Let's see if does Control Z work. Oh my God, it does. Thank you, Mara. Okay, how about pink? Pink works, right?
Oh, there you go. Yeah.
Cool. So Go routine 2 sends channel 1 foo, and Go routine 3 sends channel 1. Let's say fa. And I'm going to sketch something that looks kind of derpy, but this is actually a pretty common pattern. Done. And we can go over maybe some other ways we can improve this, but this is sort of a common paradigm. And let me use a different color here. And so we can kind of envision this process where you have, maybe 1, 2 into infinity different Go routines who are sending things to a primary source of that processing. Again, this is sort of like effectively a queue, except in Go world. There are other types of queues, but it's not terribly important. But this is really sort of easy to visualize. It's really easy to think about. I send the doer or the processor a thing, it sends me a done. I send it another thing, it sends, that arrow was in the wrong place. Oops. There we go. Just pretend that doesn't exist. And then it sends a done, right? This is a pretty sort of standard practice. But when you get started with Go, one of the things that you can kind of get into trouble with, and I'm going to use this color green here, is that you can have these long periods, and green here, where there's effectively a lot of waiting or blocking. because even though it's concurrent in that you can kind of send things to different, you can send messages through channels to other routines, the default sort of idiomatic way to handle that is to wait for an incoming message on that channel. And so there's a lot of blocking, but Go makes that okay, because the Go scheduler effectively knows how to handle, well, this is blocking, these are blocking, this is blocking, but none of the things are really blocking at the same time. And so it may, because it knows, sort of the how small these things are and things like that, it's able to run this all in a single thread. All right, and so this could be thread. I'm sorry about my handwriting. Oops. This could be oh no, that's not what I want. Bear with me. I'm sorry. Thread 1. That's terrible. But you kind of get the idea, right? And so Go, even though you're sort of like you're describing a system that has a lot of blocking or has a lot of waiting, because the blocking is happening at different sort of times, and hopefully the blocks or the waiting periods are pretty short, even though the paradigm is to sort of like wait on incoming messages and then do a thing. The Go routine or the Go scheduler will know all that stuff can fit in one thread. And so there are a series of context switches, which I will use yet another color for. And so there's a context switch here and another one here and another one here, right? And so, 2 effectively wakes up Go routine 1 when it sends it foo, and then 1 wakes up, does the thing, whatever that happens to be, and then sends it back to 2, which has been basically asleep the entire time. And so hopefully this kind of like a super high level sort of explanation of why blocking and waiting isn't terrible in, say, Go world. Whereas if you were to, if you're coming from future or promise world, you don't want your futures to block ever. That's extremely bad. Don't do that. In Go, it's kind of the common or it's the idiomatic way to implement a lot of concurrency patterns because the Go routine knows how to context switch effectively. And so hopefully this diagram makes sense. Any questions about this?
Well, that actually worked out pretty well with the little whiteboard there.
Yeah, and I think you said there are different patterns as well. This is sort of like, I like to use the cube as sort of like the first example because it is something that exists in every single language. There's a pattern. Mm-hmm. This is kind of a way to do that in Go, and it looks terrible from sort of like from a traditional concurrency perspective, but it actually ends up working out very well because the Go runtime does its job pretty well. And so this also, it looks very, very similar to the actor pattern. And so if you are familiar with the actor pattern, well, I think technically this describes the actor pattern. And the reason why, let me see if I can find where is an eraser. There it is. Cool. So that's not what I wanted to do. Oh, okay. I am learning this as we're going. Nope, I don't want that. Okay. Let me see if I can, a white pen. That's an eraser. Okay, apparently the background isn't white. Yep, we're doing it. Let's go with it. And so the reason why this, why Go isn't typically described as actor, and this is a really, really tiny point here. If we go back to the example in here, notice that we haven't really, when we create a Go routine, we're not naming it. We're not creating really anything that is, long-lived. We're saying, yo, Go function invocation function I, right? And so we're using the function invocation itself as sort of the context for that routine. Once that function is done, that Go routine goes away. And so the difference here between, say, Go routines and the actor patterns is that Go routines themselves aren't named, right? They're not, they don't really exist as any sort of thing that you can move around. And while they do take up some memory, they're not, they're not named actors that stick around and can live into perpetuity, basically. And so back to the whiteboard, this is actually probably more of what you would see in idiomatic Go, where you'd have a Go routine 2, which would do some calculation, figure out what to send to doer 1. It would return, done, maybe check the return, and then it's done, right? It's over. The lifetime of 2 ends here because it's fulfilled its purpose, right? And then same thing with Go routine 3, do some calculation, figure out what to send to 1, fa, it would get done or some error back from doer, and then it's done, right? And so going back to like the whole blocking, non-blocking thing, because Go routines typically aren't long-lived, and the lifetime of them, they're not special. You can create as many as you need, and you can, once they're done, they're done. The blocking that exists on a single, Go routine is usually pretty short. It's not something that, you have to necessarily you have to perform any complex scheduling around, because idiomatic Go routines don't live very long. And so you wouldn't ever really want to do this with threads, even with the thread pool, because it would be extremely expensive to do. But you can do that with Go routines because all of this, for instance, it's happening in a single thread, and Go knows how to handle the context switching internally. And so, yeah, that's sort of the primary difference between Go and sort of the actor pattern. If you've used actor patterns in other languages, actors typically are named, they're long-lived, and they often sort of represent sort of like business ideas, if you will. So people or systems, sort of like domain-specific things. Like you wouldn't necessarily create a Go routine named after, principal architect or something like that. But you can, that's a terrible example. Hopefully that makes sense, right? So actors are named, and they typically represent something in the domain space that you're using to concurrent size or make concurrent. Go routines typically represent much smaller ideas because they're functions, not objects. And so slight sort of like caveat, but it's actually kind of important when you're thinking about how to use Go routines in practice. That's pretty much Go concurrency. No, really, it's kind of like explaining Go routines and the channels. How you make the channels is kind of less important if you're beginning. But the only thing that I would really, the only other thing I would mention here is that there are ways to block. So again, if you're waiting on a message, this waiting on a message from a channel will block. But again, because we know the Go runtime is very good at what it does, it won't actually block. It'll just context switch to do other work. And yeah, there are buffer channels. That's not terribly important. But if you're familiar with like thread joins and things like that, those constructs also do exist in Go. So you can join on multiple routines and things like that if you need to. There are weight groups in Go.
Yep.
What else? That's pretty much it from like the basic sort of construct or the basic sort of primitive perspective. Because I didn't mention mutexes or anything like that. I guess that's actually probably an important point. Because Go is very much sort of like copy all the things by default. You can imagine a system like this where if I'm sending a string foo from use my mouse from Go routine 2 to 1, it's actually, it's copying, well, that's foo is a string, so it's a move. You're moving the pointer. That's not terribly important. But say this was an object or something a bit more complicated. Channels, and hopefully it goes over here, that and here somewhere as well. Maybe. This goes over channel direction, and not really. Well, Go is one of those languages where you don't necessarily have to worry about whether something is copied or whether it's a pointer, unless you run into issues. Go channels really aren't any different. And so if you're sending data from one Go routine to another Go routine, unless you're using references, you don't really ever have to worry about what happens if Go routine writes to this thing that it just got. It won't affect anything in Go routine 2. And so mutexes are typically used when you need, again, to prevent data races and things like that. If you're using concurrent, Go routines in sort of like the basic sense, you don't necessarily have to worry about data races. That's not always true. But if you stick to sort of like the basic primitives of channels and Go routines, you don't really have to worry about that. Where it gets really complicated is if we have multiple channels trying to access the same, or multiple Go routines accessing the same data at the same time. So sort of the same sort of, maybe I could draw that. Yeah, let me add. Let's add something. Let's call it. It's blue. Here we go. DB. Woo. Say we have a database that Q1, or say that the well, how would I explain this? So if database is used by all three Go routines, and the database is not able to be accessible concurrently, you have to figure out some sort of locking construct to prevent 1, 2, and 3 from sending events at the same time. So you would still, in this case, use like a mutex or something like that. Those do exist in Go. If you do need to, if you have either external resources that don't allow for concurrent access, or if you really do need data to only be accessible by one Go routine. But these sorts of things aren't necessarily the norm, right? These are kind of cases where you're dealing with the file system, external databases, things like that. You don't have to worry about those sorts of things when you're dealing with, typical data passing in between Go routines using channels, which is really nice. That channels facilitate that pretty well. I think that's pretty much it. Unless you have anything to add.
Yeah, no, that was actually really good. It's like Brandon was able to finally make it. And then here we go.
Yeah, I was actually working on some Java stuff for work and didn't realize it was well past 6.
Yep. It happens. Well, you get to see my lovely diagram here on Miro. Miro is great for like whiteboarding, and you can have as many people join this one screen as you want and create different layers for each person, so you never really like run into like erasing someone else's stuff. It's really good.
Pretty cool.
But yeah, so we kind of just went over at a high level Go concurrency. This is my pretty little diagram here, and the miracle of all of this happening in a single thread. Yay, Go. Yeah, I mean, I think like for the more sort of like curious folks, if you're interested in like how the Go runtime schedules things, again, it's kind of, I don't want to call it work stealing, but it is, if you're familiar with that terminology. And it isn't deterministic, but neither is like the C++ runtime. And so the order which 2 or 3 are actually run, for instance, if you were to run the program multiple times, it's not something that you can predict, right? And so you can't rely on ordering of any particular process. Everything is done in a fairly asynchronous way, and it's, you'll notice patterns, but that determinism is not guaranteed by the Go runtime. And if you mention that, if that's the source of your problem, experienced Gophers will roll their eyes and tell you that it's not deterministic and you shouldn't do that. Yeah, so those are sort of like 2 other notes I would mention, because like some systems, again, like promises, they're state machines, so things can only go in one order typically. Goroutines and Go concurrency is not order dependent for the most part.
Yeah, we got a question in here, and then it sounds like that David's in the same boat as I am. He's got, in my experience writing HTTP services in Go, never found the need to directly use concurrency primitives. Where it mattered, they were used either by libraries or HTTP and DB drivers. Mm-hmm. Is that typical, or is he doing something wrong? Or I should say, are we doing something wrong? I'm in the same mood, David.
No. So when you're, when you're the user of a library that uses concurrency underneath it, and this is also a little bit different from using a future or a promise, right? The operation that you call, say, get user from from database, it may have concurrency underneath it, it may have Goroutines underneath it, but that concurrency doesn't leak into the public-facing API. That's not true with, say, promises or futures, which, if you're used to async await, like you would still have to then await that get user, either using an await syntax or .await. That leaks that concurrency into the public-facing API. Go doesn't do that. There's no way for Go to do that. You can't leak the concurrency into the API itself. And so, yeah, it's nothing. It's idiomatic. We're not doing anything wrong but what it can create is, if you were to say like map the actual call graph of Goroutines in your program, it can be extremely complicated, like extraordinarily complicated to debug, because underlying libraries have their own sort of patterns, and those libraries are calling other libraries which also have a bunch of Goroutines, and so there's like this ever-expanding web of concurrency, and there's typically not instances where they run into each other, but if you're dealing with things that are touching the file system or even network resources, sometimes there may be race conditions in there that good luck trying to figure it out, right? And so that's one of the downsides of sort of that pattern, versus using, again, a future or a promise sort of based thing, because it's a state machine. Everything has to happen in an ordered way, for the most part. So yeah, typical. There's no way for that concurrency to leak for you. But you can still use those libraries in Goroutines if you don't want to block, right? And so if get users is, uses a bunch of Goroutines underneath, it's still going to take some time, potentially, depending on network conditions and things like that. You can easily turn that into go get users, and then, follow up or go get user function that then calls get user, right? So effectively, you can choose where you want to block and where not to block. In other paradigms, you don't really get an option.
Good. So I don't have to give up on Go myself then? I can,
no.
I can still be allowed to play around with it.
Yeah, it's something that isn't ever required, right? You don't have to, your Go programs are going to run just fine without concurrency. It's not like you're going to run into any issues where you can't functionally do something. But Goroutines are there where either you don't want to block, or because there's long-running operations, or it just might be cleaner to sort of architect your application in terms of Goroutines. That, I think, can get very messy, and that's, again, where you're kind of treating Go in more of an actor type way, which you can do. But you just have to understand the limitations from the scheduler if you're going to go that route. Cool. So yeah, totally normal. Like if you were to see some of my like basic sort of HTTP services in Rust, there are concurrency primitives literally all over the place. So it's a very different experience. Lots of await and async, and it's a very different thing.
It's a lot lower level in that.
Even so, I would say, like, even if you're working in something like JavaScript or any other language that uses async await, like even some of the higher level languages use async await, you would still see sort of the same thing where you have to call await in an async context, and that async context has to flow up towards main, wherever that happens to be. And so Rust isn't unique in that. And again, there are some benefits to using it that way. It's a bit easier to debug and track down issues. And it's, when done well, should be higher performant. But again, if your future is block, or if you're insert any number of things you can do wrong with implementing promises or features, your performance tanks. So Go is much like it's everything else in Go. It's reasonable sort of default for the intermediate or sort of like common use case. If you're trying to do anything funky, the primitives are there to implement. You don't have to use Goroutines. You can use threads if you want. But yeah, it doesn't offer you much help if you were to try to go any lower level than that.
Cool. Trying to say, it doesn't look like well, there was one other suggestion that I added to the coffee table there. But somebody had already written up writing security specific test cases.
Yes. Oh, generics. I don't want to talk about that. Someone else.
No, that's what I grew up there. Come on.
No.
Just what do you know about those things? So,
yeah. I mean,
there's an article that I haven't read yet about some of the generics, or how I guess they're envisioning the use of them. But I did not get to go through it, so I definitely don't grok the whole concept and Go anyway. So
yeah, it's this can get super nerdy, but there. Because people are talking about, so right now, if you want anything that resembles generics in Go, you're effectively using a preprocessor, right? So something that generates a bunch of code for you from some types that you want to support. There's quite a few out there. Kubernetes has one internally, and it's crazy. So people are kind of like trying to create their own metaprogramming on top of Go. There isn't any real standard. That isn't generics, right? That's templates, effectively. And So when people are talking about generics in Go, they're trying to get away from templates and into sort of like proper generic support that has like all the runtime type introspection and all that great stuff sort of working. And the very long story short is that they're trying really hard not to dramatically increase the compile time of programs that use generics, which is typically what happens, right? And so Go's type system isn't terribly complicated. So because a lot of folks are using interface for things and yada yada yada, like so a lot of the type checking is actually happening at runtime. If you use type switches in Go, that all happens at runtime. So generics in Go may force a lot of that type checking to happen at compile time, unless you want some really, really, really nasty runtime type stuff that can make the language a lot more unstable than it already is. So it's a very rich debate. I have opinions, but I do. But they do have some legitimate points. Like Go right now, which is very small, and it's very lightweight. Actually, let me. I have an idea for. Do we have time for another whiteboard? Absolutely.
I think we're set up for 2 hours. So
okay.
The clock on the wall there says that we've been in 1 hour and 1 minute.
Okay, so let me. I guess I can save this. Is that useful? Sure. Let's create another one. It's fine. I need to pay the money, apparently. Cool.
I also asked one that I'd been wanting to ask since this was scheduled.
Is it not generics? Okay. Cool. What's there? Writing security test cases. We can talk about that quickly afterwards, I guess. So, yeah. So there's kind of, I won't go too far into programming language theory world, but this is kind of where a lot of the stuff falls down into. So I'll try to keep it high level without boring everyone, maybe. I don't know. But so I'm just going to just talk about maybe like the two different ways we can kind of do this, right? And so let's say we want to implement what's a good example? A linked list, right? So we want a linked list to be able to accept different kinds of types. So let's just do, so we have list, and I'll use the syntax people are probably familiar with, type T. All right, cool. And so we have a list of T. That's not true, but so we have a list and we want to implement a list of T. So the language community has a huge number, technically, ways of supporting the list of type T. And so the two ways I've seen discussed in the Go generic sort of implementation debate. One is where you compile, and I'll kind of draw that here. So when you compile list of type T, let's say we have in line 40 of some file, we have make. This doesn't make. I don't know what the syntax actually looks like. It won't look like this, right? But let's just pretend. And string. So we have in our file on line 40 somewhere, make list string. And so we know the compiler knows that this program has to support list of string type. If you come from C++ like I do, you would know that the preprocessor, although that changes now, is very complicated now. But 10 years ago, C++, the preprocessor would look at this and say, okay, well, list of, bracket, yada, yada, yada. I'm going to generate a lot of code at compile time before sort of like the main sort of compiler runs. And you end up with some list underscore string underscore 1000 blah, 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 blah named thing. If you've ever looked at the C++ exports when you're using templates, it's terrible. It makes everything really complicated to debug. And so a lot of languages have moved towards, well, I'm going to, instead of generating a bunch of code prior to compilation, I'm actually going to generate list T. And you can imagine a bunch of methods that will work on any T. And then over here, let's do a slightly different color box over here. I'm going to, if need be, specialize methods that work on list string. And this overlap is kind of terrible, but and so it'll then generate this container. This isn't the proper terminology, and this at compile time will be list T. And so we'll have some methods that will work on lists of any type T, and then we'll have some methods that'll work only on string, either because they're specialized or because string has to be handled in a very specific kind of way. And so this is, but all of this happens at compile time. Right. And this process is called monomorphization. And if you have a background in other languages like Rust, for instance, this is kind of how that works for the most part. All of this type checking happens at compile time. And what it kind of allows you to do is maybe you don't want this to work with, say, any T. You want it to work with some T. And, so I want list to work with some T, say where we know the size of T at compile time, which is, a perfectly reasonable thing for a list to need, right? You're trying to store T, you have to know what the size of T is, right? And so you may have some restriction. List here works for some T. We have some method that works a list for list string. String is sized, so it type checks. Woo, we can do all of that stuff at compile time. It works, right? And so that's sort of like, again, this is the typical way. This part here, the where T is sized, this sort of like constraint, and the some T here, you will see a lot of folks in the Go community who don't like this, right? Because right now there aren't any traits, for instance, which you would see in this sort of process. And as soon as you add stuff like is sized, the complexity of the language blows up, right? And so the Go community, doesn't typically support these things and are instead supporting NAT. So hopefully that sort of makes sense. And so this all happens at compile time. And again, this process is called monomorphization. And if you've, again, used Rust or another language like C++, modern C++, a lot of the compilation time is this, because we're using generic structures, and you have to make sure that all the constraints themselves work, and you have to generate methods specifically for types if they're different. And then there also may be specialization involved. So over here, I know, I wonder how many people have left. I can't tell. So let's do the same thing over here, right? And so we have on line 40, the string, boop, right? And so there's another way to do this that relies way more on runtime type information, right? And so we'll start here. Oops. And say list again of t, and we want this to be supported for any t. Cool. And so this is not at compile time, but this is at runtime. And so that'll help provide some context here, maybe, or RTTI, or type introspection, or any insert term here, right? So, but generics typically refers to runtime specifically. So we have list t, we have any t, all right? And what happens, this is all that exists at compile time. And when you get to line 40, and maybe you do this pretty often, maybe you don't. But say we run the program main line 40, make list of string. Say, well, okay, the program or the runtime knows, and it often requires some sort of runtime in the background to do this sort of type checking, or some interpreter. And so interpreted languages work this way a lot, where let's say the runtime or the interpreter says, okay, well, you're trying to make a list of type string. I have this, you can think of this sort of as a recipe. And so I have this recipe for list t where any t, and there's some methods in here, right? So I'm going to then take this and let's use the word render here to list string. And I'm going to perform this sort of like overlap here, right? So I have to determine what can be used, what can't be used, what needs to be specialized. All of this stuff here happens at runtime. And then, of course, once it's figured out this new sort of new recipe, let's use the word recipe, it doesn't have to perform this again for a list of type string. And so here's another recipe. And so this happens at runtime. And the cool thing about this is that the compile time, you're just creating the recipe or the template, and you don't have to perform what type checking to actually compile or assemble the program. Because, again, that assembly of the recipe happens when it gets to the line. So when it says list of type T, say at some point say this is Python or say this is Ruby, where you can kind of create new types on the fly because, you can, right? The compiler wouldn't know the entire universe of type T, right? And so if this were, instead of make list type string, if this were make list of I don't know, say foo, but foo was created on line 25, type foo, I don't know. Well, that's not a good example. Let's say at some point we created type foo, because again, in certain dynamic languages, we can do that. Type foo didn't exist at compile time, but it exists at runtime. And so I need to be able to create a recipe that can support types that aren't known at compile time. And so for those kinds of languages, you kind of have to do this, right? At compile time, we have to know all of the types that the list has to support and generate, figure out, that sort of overlap, if there's any specialization, figure out if there are any constraints, which again, Go doesn't necessarily support. But if there are, making sure that these constraints are in fact met. And if it doesn't, then there's a compiler error. So this sort of polymorphism, if you will, requires some runtime type information, but it also has to support sort of, again, like types that are generated at runtime. So if you know anything about sort of the weird advanced use cases of Go, you can create Go types at runtime. And you can do a lot of really weird things with runtime type information in Go. And this is forcing folks to kind of more over here towards this runtime implementation of polymorphism, because Go has a lot of runtime type facilities that if we were to do it at compile time, this wouldn't work, right? It would break. So that's sort of we have a bunch of people approaching the problem from these, a couple of different ways. I'm, used to languages on the compile time side of things, but if you're again from a Python or Ruby background, you may be used to things on the right side of things. Go, unfortunately, kind of attracts users from both of these camps and, both of these different kinds of backgrounds. So how to implement this, it has been a very furious debate that I haven't gotten involved in because I don't really care. But it does change sort of, how the language will feel, because on the left side, the compile time sort of monomorphization will increase the compile time period. And people are, again, very accustomed with Go being very quick and very small. And you can imagine that if there were a list of string and then a list of int and then a list of whatever here, the other thing that this does, that's a terrible color, is that, we have some other type here, and then we have some other type here, and then we have some other type here, and then another one here, right? This increases the size of the binary. So every time you have to perform that sort of let's make a list of a new type, it adds new methods. There's effectively a lot of copies in certain cases, and that increases the file size. Here, because you're only compiling the recipe, there's no real change to the compile to the compile size of the binary, which is good. But again, this arrow here represents something that's computationally expensive. Let me see if I can. Here, this arrow here, right? And so because you're performing this at runtime, there is some cost associated with the first time you call make list string. It's not a lot, but there's some. But if there were some, say, constraint, and where it's not any t, and now it's some t, right? And where t is, whatever, there's a possibility for this process here to fail at runtime. And so if I were to try to do this with type foo, and type foo doesn't meet this constraint to be put in the list, you're going to end up with some sort of runtime exception that you then have to figure out. And right now, Go doesn't really have a lot of runtime type errors, unless you're really in, like, you're using some of the runtime type in. If you're using some of the RTTI packages and things like that, you may run into some type issues, but that's not typical, right? It's not, you typically don't get into that circumstance, even when you're using type switches. This would create potentially, if someone, again, created a type foo at runtime on the fly, and it doesn't meet some constraint for list T, you have to handle that error in a meaningful way, and type exceptions like that are extremely difficult to handle. What do you do? I can't create a list of this thing. How do you sort of proceed with, how do you recover? There's no recovery plan from that sort of thing. And so a lot of folks are very much on the camp of, well, even though this creates something, the left side creates something that's bigger, it increases the compilation size or time and increases the compilation size, the binary size. I know of any type errors at compile time, and so I can't distribute things that are going to fail in the application. On the right side, you can very much write code that you won't know isn't going to work until you run it. Which again is why this sum T or any T, people don't want that. We're trying to they're very much opposed to that sort of thing, because it can run into a circumstance where there are runtime type errors that aren't going to be recoverable. So if you're coming from a C++ background or a Rust background where you can restrict, like there's concepts in C++ now too, which are definitely not getting into that, or Rust traits where you can really create containers or different sort of like generic structures that only work for certain kinds of things. Don't get your hopes up if that's what you're expecting from Go. The generics that they're sort of explaining that people tend to be arguing or moving towards are going to be very, very, very simple, because the type system simply isn't really sophisticated enough, and people aren't wanting to get rid of their really short Go compile times. So hopefully that's useful. But this, from my perspective anyway, this is sort of like the generics debate, and at some of the more fundamental issues, it's not that folks don't want generics. At this point, I think they've said pretty strongly that generics are coming. They're kind of arguing over the semantics and stuff like that. And again, some of the programming language theory stuff isn't terribly important, but it can, and it probably will change some of the how do you use this language every day type thing.
I don't know. That was good. Thank you. Yeah, I mean, I didn't think it was. I didn't realize it was such a big the battle between compile time versus runtime on that. On the implementation for it.
Yeah, it's not necessarily the battle between these two things, but I think fundamentally a lot of the arguments people are making are because they lean in one of these directions, right? So they're not like arguing compile time is better. Like, well, no, it's not what they're saying. They're a bit more sophisticated than that. But there is like, I don't want to introduce additional type exceptions effectively at runtime because we don't really have many of those, and the ones that Go does have aren't necessarily recoverable, and it crashes effectively. There's nothing you can do, so we don't want to introduce that instability. And so those are the sort of arguments that you will hear. Again, personally, I don't have a huge stake in any of this stuff, but a lot of the arguments are based on sort of preference towards one of these.
Yeah, no, that's good. Thank you. Yeah, it looks like Brandon snuck in a question here at the end about the usage of content.
I actually did it before we started that, but about half an hour ago. Kidding. No, it may be a simple answer. It could be another one of those though. So I don't know. So feel free to answer it on the side sometime if we're.
Is it on the board or somewhere else?
It's on the question. Well, I don't know where it went, but.
Oh yes, it's in the ask a question. Oh crap! Did I? Oh, there it is. It's in the answered section.
Oh
no!
Wait, here.
It's basically. A year ago, I did that presentation on managing context through concurrent, applications or whatever. But you mentioned that context was no longer an encouraged pattern and Go. What are people doing to replace that?
So I'll answer that with that's not really what I said.
Okay.
So
I oversimplified it to
So people are still using context very much. A lot of people have problems with context. I think I'm coming from the perspective of shared state being very bad generally, and I say that because it's kind of an anti-pattern. It's also kind of an anti-pattern in Go concurrency itself because, channel-based message passing based concurrency really is trying to avoid sharing state. You send what you need and you get back exactly what you need. But unfortunately, you do need context-specific information often to determine what to do with that one piece of that message that you received. And you don't want to necessarily parameterize, 18,000 things just to get context to this one Go routine. So I won't say that it's being discouraged. It's still kind of the idiomatic way of doing things. You see context all over the place. But folks are kind of acknowledging that there are a lot of problems with it. Context often sort of require runtime type information to be useful, especially if you don't know what the types are going to be at compile time. And if you're getting them, there's like serialization and deserialization issue. It becomes kind of a dumpster fire. It's sort of like the too long didn't read version of that. So I don't know if there's a sort of a good alternative right now in the Go space, except that a lot of people are complaining. And then people who have like functional programming backgrounds are eye rolling very much with the idea of shared state. And then, it's, I don't know how to answer your question. Let's put it.
I think that's good enough. That kind of explains where you're coming from. That that's all I really. I'd been asking myself for a while and trying to remember what you'd said exactly. So.
Yeah, I mean, if you use context and you don't want to necessarily run into a lot of issues, like you're creating a bunch of copies of things, and from a memory-based perspective, that's not necessarily very good. But also from a data ownership perspective, there isn't any, right? There's no real way of like tracing the data, the ownership of any particular data in a context back to where it originated because it's just copied into infinity, right? Does that matter to your application? Maybe. I typically, I dislike that sort of thing very much because context can be changed in the intermediate, and you can't necessarily trust the information in your particular copy of the context because it's mutable and there's no ownership. So yeah, I think you would hear more of that debate in like more of like the programming language theory community and people who are in the functional programming community who are going to Go for some reason.
I gotcha.
Yep.
When do we have to cut this off? Is it an hour and a half? Because if so, we have 30 seconds.
No, we get to we have about a half an hour.
Oh.
Yeah. So
you have time for one more whiteboard.
Yeah. This is I'm gonna keep this one. But yeah,
thanks for keeping it high level. I appreciate it.
Yeah, this is about as high level as I can possibly do.
Yeah, no, that was really good.
Yeah.
Yeah, there are sort of like formalizations to all of these things. I may send a link to it, but if you're interested in type theory and polymorphism and the different ways you can do this, I will probably post a link and meet up later if you care. But yeah, the polymorphism from a type perspective is actually quite interesting, and there's a lot of different ways to implement it without using symbols like this and blah, blah, blah. Anyway, I won't do that. What else is here? Writing security specific test cases. I'll answer this very briefly. There's actually a guide going around on Go application security. It's from a vendor, but it's surprisingly good. And so I would direct folks to that one. Yeah. Honestly, like a lot of the, like I'm writing security specific test cases right now. They're all, for the most part, in Cucumber, right? So we're not necessarily writing them in Go, but we're testing like crypto workflows or like user authentication and stuff like that. But we're using some sort of like Gherkin syntax and some high level testing framework to do that with. Yeah. There is a book called that's not useful.
It's not covered in Gray Hat Go, is it?
No. Yeah, Agile Application Security. If you are looking for a book that's not Go specific necessarily, but this is probably the best example of a book that would get you into, like, if you want to do BDD or behavior driven development, which is effectively Cucumber or in Gherkin syntax, that sort of stuff. If you use RSpec before, there's some other Cucumber like ones I don't remember. But if you've ever used RSpec or Cucumber testing framework for your application, you can do that sort of BDD from a security point of view. And so there's, I think there's a whole chapter actually in here somewhere. But yeah, there's definitely a lot of content in here about writing BDD tests from a security perspective. So buy the book and apply them to your Go programs. But yeah, a lot of the, if you're a security engineer, a lot of the things that you're going to be dealing with from a security perspective aren't like make sure this function returns what I expect it to, because you're not typically operating at that level in the program. You're more concerned about workflows and sort of higher level concepts. But if you are sort of like testing crypto primitives and stuff like that within Go, there are some decent ways to do that. I don't know if a good reference for it though. But yeah, I'll also post the link for the Go application security ebook. I found it pretty useful. Yep.
Awesome. Here, I'm gonna switch over in the slides. Let me share. Crap, where is it? Get our outro going here.
Cool.
So yeah, no, thanks very much, Sabri. It's always a good learning thing when you're up there talking. So, but yeah. So anyway, yeah. Anybody that's left here, please do let us know how we're doing. again, any other topics that you might want to talk about. Sabri is our local cloud native computing foundation ambassador. So, thought about maybe getting some other CNCF projects discussed on here. So, ones that are obviously written in Go. But yeah, no. Of course, the little ad here for the St. Louis Tech again. Join up there. Don't isolate alone. And then we'll have next month, May 27th, Daniel Magnum. I keep messing that up. Mangum writing general purpose Kubernetes controllers in Go. So that should be pretty fun. So that'll be an interesting one. He does a lot of speaking. He even hosts a bi-weekly video cast for Crossplane. I always forget the name of that thing. So anyway, everybody, thank you for sticking around. Apologize for the difficulties we had last week. And we'll look forward to seeing y'all on May 27th. So have a good one. Stay safe and stay healthy. See you guys. Bye.